All right, here we go. Today is lesson 2.1, starting a new chapter. Today's goal is to describe patterns and use inductive reasoning. So geometry deals a lot with logic and logical thinking, trying to improve that part of your brain. As sophomores, that part of your brain is still developing, so this is a really good lesson to try to improve that way of thinking for you. First little term we got to discuss is conjecture. Who can tell me what conjecture is? Yes, sir. I saw your hand. An unproven statement Good call, good call. It is basically a hypothesis. So it's an unproven statement based on observations. And a hypothesis is a good way to think of it. Kind of making a guess at what's going on. It's more of an educated guess. So please be aware of that. Inductive reasoning. Reasoning using what? There's a key word, starts with a P, patterns. So reasoning using patterns. And we should be really good with patterns, numerical patterns, pictorial patterns, and things like that. The last little term is counterexample. Counterexample. What's a counterexample? A specific case that shows a conjecture is false. And we'll see some examples of that here in just a little bit. Counterexamples are pretty cool. You're good at these. If you're good at arguing, you will use counterexamples all the time. Lawyers use them all the time. So if you're good at arguing or you like arguing, you already use them. It's just seeing them in terms of math. In example 1, it says, describe how to sketch the fourth figure in the pattern. Then sketch it. So it wants a description. So let's circle or underline that word. A lot of people miss that word. It says describe and then sketch it. So look at the picture carefully. I'll give you a second to look at it and see if you can figure it out. All right, who can give me a good description of what they think's going on? All right, go ahead. Each rectangle is divided into half. What'd you say? Each rectangle is divided half of every figure. Can anybody give me a little bit different example? Yeah. Okay. I'd be careful on saying adding 2 to each one because they're not really making it any bigger. So tweak it. Okay. Okay. They're dividing it to where it's 2 extra sections in each shape. Any others? That's a pretty good idea. So it can be verbally written in a lot of different ways. They say each rectangle is divided into, yeah, it's not exactly 2 times as many, so be careful. It's really adding 2 more specific sections inside, specific divisions inside the shape. So let's see if we can draw this real quick. So we have our rectangle. We already know that we have a horizontal line through the middle. But then you got to determine how many vertical pieces to draw. Here we had 0 vertical pieces. Here we had 1, 2 vertical pieces. This one's going to have 3 vertical pieces. All right. So now the key thing, though, we didn't describe this, is about shading. There is a shaded section in each of those. Which one should be shaded? Always shade the bottom left region. And that's a pretty decent picture. Good job. Take a little time and try the next checkpoint. It says sketch the 5th figure in that example 1. Good. It looks like everybody's doing well here. Once again, we have our rectangle. We know we have one horizontal line going through the middle. We had 0 vertical lines, 1 vertical line, 2, 3. This one's going to have 4 vertical lines. So, 1, 2, 3, 4 vertical lines. Oops, I didn't go down all the way, but I think you get the idea. And shade in the bottom left region. So I'd say the most difficult part of this type of problem is the description. It's kind of hard to describe sometimes, so we'll be practicing that. On example 2, it says, describe the pattern in the numbers -1, -4, -16, -64. Then write the next 3 numbers. Once again, it has 2 goals it wants you to do. It wants you to describe, then write the next 3 numbers. Can anybody obviously tell what it is immediately, really fast? Let's see who, go ahead. We're multiplying by 4. So the key thing, each of these terms is multiplying by 4. Good job. So then you can calculate what the next 3 terms are. Try that real quick. So what do we get for this next term after -64? -256, followed by -1024, and then 4096. Good job. Good job. I like this next example a lot. Example 3 says, given 5 non-collinear points, points that are not in a straight line, make a conjecture about the number of ways to connect the different pairs of the points. So here, in this first picture, we have 1 point. How many different ways can you connect to another point? There's really no other ways to connect any other points. But now we have 2 points. How many connections are there? There's 1 connection, 1 little line segment. When we have 3 points, how many connections are there? 3. Now count carefully on the 4th one. With 4 points, how many connections are there? 6 connections. Now, 5 points. How many connections? I see 5 around the outside, 5 in the middle, 5, 5. That's 10 total connections. The goal, though, is to determine the pattern. How much are they going up by here? They added 1, added 2, 3, added 4. How do you describe that type of pattern? Adding is what you need to start with. That's the operation. So we are adding sequential, or consecutive is a better word, consecutive whole numbers. That's a good explanation. Just what the book will say as well. Try the next checkpoint on your own. Real quick, it shouldn't be whole numbers. Whole numbers has a 0. It should be natural numbers. Natural numbers starts with 1. That's what you learn when you're a little kid. In checkpoint number 2, the question says, describe the pattern in these numbers and write the next 3 numbers. So what's going on in this pattern? They're adding 1.5, so you could just simply say they're adding 1.5 each time. What are the next 3 numbers? 7, 8.5, and 10. Good job. Number 3, checkpoint 3. It says rework example 3 as if you're given 6 non-collinear points. So instead of just having 5 of these little dots, we're going to have 6, and it would look like this. Now you have to think about your number of connections. So you should be able to count as I'm drawing. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15 connections. Did the pattern hold true? Yeah, it added 5, increasing by consecutive natural numbers. Good job. On example 4, it says numbers such as 1, 3, 5 are called consecutive odd numbers. So I've already talked about consecutive whole numbers. Now we're talking about consecutive odd numbers. Let's underline that phrase. That's a good phrase to be able to write. Consecutive odd numbers. Sometimes we have consecutive integers or consecutive evens. Those are when they come one right after another. It says make and test a conjecture about the sum. What's sum mean? When we are adding any 3 consecutive odd numbers. Any 3 consecutive odd numbers. So let's look at that. They give us some good information here. So here are the first 3 consecutive odd numbers. 1, 3, 5. What happens when you add all of them up? They come out to 9. Let's look at 3, 5, 7. 3 plus 5 plus 7. What's that come out to be? 15. Well, what they realize is that these are both multiples of 3. 9 comes from 3 times 3. 15 comes from 5 times 3. Now, if you look at this and look at these numbers, you should notice something. So a key conjecture would be the sum of any 3 consecutive odd numbers is 3 times the middle number. Good job. Good job. The key thing on creating and testing a conjecture is you really need to do at least 3 examples to prove it. We've done it twice. Let's do this third one as well. 5 plus 7 plus 9 is 21. That comes from 7 times 3. Is that the middle term? Yes, definitely. It still works. So you need to do it not once, not twice, at least 3 times. They do it a 4th time. I'll say 3 should be enough to prove your conjecture. Good. All right, this next one you have to read carefully. It says, make and test a conjecture about the sign of the product of any 4 negative numbers. I'll help you out real quick. The sign means what? So it's positive or negative. Positive or negative. What's the product mean? Multiplication. Any 4 negative numbers. Any 4 negative numbers. So you should be able to come up with that pretty good. Create at least 3 examples. Make a conjecture and test it. Try that. All right, let's try this out. Somebody give me any 4 negative numbers. Go. Okay, I definitely wouldn't pick numbers that big just because you get a big product, but that's okay. It's good to test different types of numbers. What's the product equal to? 7,792. Somebody give me 3 others, hopefully smaller. Yes. Smaller. Go. So he kind of used the numbers from earlier, that consecutive odds, but as long as they're negative, it doesn't matter. And you got what? 105. I need another, one more set. Now, one thing I would note about these last 2 examples, I would make them more random. Personally, I would try to make them more random to make sure my conjecture is solid. What do we get when we total those up? 24. What do we notice about all those products? They're all positive. What else did you say? Okay. The key thing is that they're all positive. That's the conjecture right there. So here's what we do. We still, some of the wording from this example up here, or from the question. It says, the sign of the product of any four negative numbers. That's what we write. The sign of the product of any four negative numbers is what? Is positive. And that's a good conjecture. Example 5 says that a student makes the following conjecture about the difference of two numbers. Find a counterexample to disprove the conjecture. First off, what does difference mean? Subtraction and two numbers. Okay, so that's pretty simple. They say the difference of any two numbers is always smaller than the larger number. Be careful on the wording here. Let's try to disprove them with some numerical examples. So we need to be subtracting any two numbers. Give me two numbers. -4 and 2. We are subtracting two numbers, any two numbers that we want. When I subtract these, what do I get? -6. Let's do another one. Be different. Choose different numbers, positives, negatives, negatives, positives. 17 minus -5. And what do you get there? We need one more little set. One thing I want to encourage you to do is try zeros every once in a while. 0 and 32 is what? -32. Now let's test it out. They say the difference, meaning this number, is always smaller than the larger number. So which one is larger in this case? -4 or 2? Okay, is this smaller than 2? Yeah, so they were correct there. All right. They said the difference is smaller than the larger number. Well, which one's the larger number this time? Oh, 17 is the larger number this time. Is this smaller than the largest number? No, we just disproved them with a counterexample. This is a counterexample. Write that down. It's a counterexample. That disproved their conjecture. Their conjecture is not valid because we disproved it. We said, hey, I can come up with a difference that is bigger than the larger number over here. We disproved them. Okay. Try checkpoint number 5 now. Read it carefully, then make a counterexample that proves that conjecture false. All right, number 5 says, find a counterexample that proves them false. We want to prove that conjecture false. This is the statement right here that we are trying to prove false. So we got to be careful. We have to understand what it's asking for first. If you can't read and understand the conjecture, you probably can't go very far. Quotient. What is a quotient? It means when you're dividing and you get an answer. It's the answer of a division problem. The answer of a division problem of two numbers is always smaller than the dividend. Well, you got to know what dividend means. Here's what I'd like you to know. When you're dividing a number by another number, you end up getting your quotients. Which of these numbers is the dividend? Which one is it? The top number is your dividend. This should help you figure out what numbers to use and what you're trying to prove. So, who has disproven this? 0 divided by 4 is not, okay, so it is 0. So is 0 smaller than 0? No, that disproved it. What's another one? -5 divided by -5 is +1. Is the quotient smaller than the dividend? No. What's another one? Okay, negative divided by a negative. Another example of proving them wrong. Good job, good job.